Good evening, everyone. Welcome to the Better Break. Tonight, we will talk about a new theory of gravity together with Professor Erik Verlinde. Mr. Verlinde, thank you for being here with us tonight. My name is Frank, and the other moderator will be Brandon. We are both part of the Better Break, which is a scientific discussion platform run by students from the University of Amsterdam. And as I said, tonight we will talk about gravity. We will roughly discuss this subject in three parts. So first of all, Mr. Verlinde will give us a short history of the gravitational theories. Then we will talk a bit more about the theory that he has been working on. And finally, we will come to talk about the social impact of such theories. And so what it means to physics and what it means to society in general. After each part, we will have time to answer questions from the audience. So we have Kim, also part of the Better Break, who is monitoring those questions on YouTube in the chat or on Zoom in the Q&A. But let's talk about our guests. Mr. Verlinde, welcome again. Would you like to introduce yourself and tell us a bit more about your scientific background?
Well, thank you very much. I'm very pleased to be here and to be, talking about my research on gravity, indeed, and trying to understand gravity at a deeper level. I'm a theoretical physicist here at the University of Amsterdam. I work on gravity, but also on quantum mechanics and the relationship with the small world, with elementary particles, but also at larger scales with black holes and what gravity does in the cosmos, because there are still all kinds of open questions there that we'd like to have answers to. So anyway, that's what my research is about. And of course, I teach also here. I'm also, actively working on these topics, and I'm happy to tell you about the recent developments in this field.
Thank you.
Professor Verlinde, when we think of gravity, we think of Einstein and we think of Newton. Starting with Newton, what are actually the most important things he's contributed to the field of physics?
Well, Newton, of course, started out understanding also what motion is about what masses are and what forces are, and he made the basis of our modern science. And the laws that he eventually wrote down still are very useful today. Eventually Einstein came and replaced his theory with a new one, but he told us basically how gravity works. And maybe I can even show this with some slides. If you allow me, I will share my screen, and I think here gravity indeed has to do with how forces appear between objects like planets. Earth is attracting the moon, and the other planets are being attracted by the sun. And Newton already knew about the motion of these planets, but he had to figure out what is the force law between those objects that have a mass. And so he figured out how things move, but also that forces make things move not in straight lines, but also make them go around each other. And in gravity, that's due to an attractive force between masses. The force is proportional to the mass itself of the two objects, but also depends on the distance. Actually, the force becomes weaker when the two objects are further apart. And so his famous law of gravity, which is written down here, tells us that the force falls off with the square of the distance. And so this equation can be used still today to calculate, for instance, how we are shooting satellites into space or going to other planets, because Newton's laws work very well at the level of the solar system. Einstein actually came along and he worried more about a very strong gravitational field, and also worried about what happens when you approach the speed of light, or when the speed of light becomes important. And he realized there's a new way, a different description of the gravitational force, which is kind of consistent with Newton's theory in the sense that it sort of still reduces to his theory when we go to the known situations, but it extends it to other cases. And so Einstein's description is very different in the sense that it goes about space and time. And what Einstein realized is that gravity is basically a consequence of the fact that space and time can be curved. I mean, there's some way that the geometry, the way that the space is depicted actually here, also as sort of as a sheet that can curve, that actually is the reason why things don't move into straight lines. So if you have a mass sitting somewhere, it creates a certain curved space-time around it that makes objects, when they start moving, go in the orbits that we know are describing the orbits of planets. His theory, as I said, is very well close to Newton's theory, but there are situations where it slightly deviates, and it also makes new predictions. One of the most spectacular predictions, which was verified quite soon, is that even light gets influenced by gravity. So here we see a picture of a mass which is curving the space, and then we look at the light coming from a far distant star, and then normally light would go in a straight line, but gravity makes the light go in a sort of curved trajectory, which means that we see objects at different points, and the light sort of bends. This is like a lens effect. We call this a gravitational lens, and they can even be observed. If you look out in the sky, you see sometimes objects that have, this ring around it. This is actually a consequence of the light bending around all of the mass that's in front of this source. So
this could not be predicted just by Newton's laws.
So Newton's law does not tell us anything about light. Light is actually not something that has a mass. I mean, the particles that are sort of responsible for light are massless even. And Newton had no theory that predicted this bending of light. So when this was observed, actually it was observed with a solar eclipse in 1919. And this was seen as evidence of Einstein's theory. It's really a new effect that comes from general relativity and could not be calculated with Newton's theory. So this is how a new theory is capable of making more predictions in other situations where the old theory kind of fails. But it's not like it's the old theory is wrong. It's basically also contained in the new theory. Another prediction, which is kind of very spectacular, which we also recently found evidence of, is the existence of gravitational waves. So that is the property that when objects, they can go around each other, and we talk about black holes in particular, which is another prediction of the theory. If black holes can go around each other and they merge, become one bigger black hole, they produce gravitational waves. And these have been observed recently, and it's a prediction of Einstein's theory that was made like 100 years ago, but it took about 80 or 90 years before it was really confirmed. So sometimes there's a lot of time in between making predictions with a new theory and for those predictions to be confirmed by experiment. I talked about black holes, and this is the other prediction that I will come back to later. Which is also a thing that we have sort of seen now with our own eyes almost. I mean, a black hole is an object where mass is concentrated so heavily in one part of space. I mean, where there's so much mass in there that the gravitational field is so strong that even light cannot escape. And these objects are also what I'm working on myself, and actually they form an important part of trying to develop this new theory of gravity that we'll be talking about today. So black holes are, for theorists, actually one of the main objects of study if you want to understand better what gravity is about and how to think about it in a new language.
I had another question regarding Einstein's predictions, because although, as you just mentioned, it makes a lot of new predictions that Newton's theory didn't predict, but what actually inspired Einstein to come up with a theory? What were the incongruencies that Newton's theory didn't explain, which Einstein's theory, which made Einstein produce his theory?
Well, Einstein knew about the fact that the speed of light was finite, and in Newton's theory, one of the things that worked well, not in the right way yet, is that the force law that Newton wrote down basically acts instantaneously. I mean, in the sense that there's a force that only depends on the distance, and when you change, for instance, the mass of one of the two objects, or you move it around, the force will change instantaneously on the other side. And so this cannot be true according to the special theory of relativity. So this is something that he had developed earlier. The special theory of relativity goes about the fact that things cannot move faster than the speed of light. And because of this, he had to modify, or actually improve Newton's theory of gravitation. And that took him about a decade, actually. From his original theory about special relativity, he went to the theory what's called general relativity, where gravity was also involved. So this is actually the summary of what Newton and Einstein did. So I will actually stop share at this moment, and we'll come back to the issue of black holes, as I said, a bit later.
Mm-hmm. So then now to the current situation, I would say, is Einstein's theory still the leading theory? Or I suppose that there are some things that are incomplete or incorrect about it.
So, well, yes and no. I mean, in the following sense, I mean, we have made a lot of progress in 100 years, but Einstein's theory does make a lot of predictions that first had to be verified, and they have been verified. I mean, like indeed what I said about understanding of the presence of black holes and these gravitational waves, and that is still described by Einstein's theory. However, we have also learned that at this very small scale that we need a theory called quantum mechanics. Quantum mechanics is about particles and properties, and they have well, very weird properties in the sense that you cannot really measure something with infinite precision. There's something called uncertainty. So when we measure something, we can only say what is the probability for a certain outcome, and not really predict the outcome indefinitely. And Einstein's theory is not consistent with this quantum theory. It's not one theory, because there are two theories, which is one is general relativity and the other one is quantum mechanics. And so one of the biggest questions, I mean, most important questions that we have been thinking about for the last 40 years is indeed how to combine quantum mechanics with general relativity. And it's pretty clear by now that requires a new theory that, well, again, will contain Einstein's theory in certain situations, but it's going to go beyond it. I mean, it's again a next step where we will have a better understanding also what space and time are, and also what indeed how we include quantum mechanics. And we are slowly and actually surely, I mean, we're making progress discovering more about that new theory. And there are certain aspects of black holes that have helped us understand better what that theory should be.
Mm-hmm. So you would say that Einstein's theory is not wrong, but a new theory would just encapsulate his theory.
That's right. I mean, it's always that the old theory is kind of contained in a new one as a special limit. And there are many situations where the old theory actually works even better, in the sense it's usually a simpler theory where you can calculate a little easier. As already mentioned, that if we want to shoot a rocket to the moon, it's sufficient actually to use Newton's theory. Although the more precise theory would be Einstein's theory, but doing the calculation in Einstein's theory would be much more complicated. So, and the same is true for many things that we are asking about gravity. It's not always necessary to include quantum mechanics. And so we can simply rely on Newton's theory or Einstein's theory, and then we don't need this new theory of gravity, and there are no puzzles to be answered. There are other situations, by the way, where Einstein's theory may fail, but this has to do more with the cosmological scales. And I'll come back to that also later, because there are still many puzzles. I mean, there are many things we still don't fully understand about gravity, which also come from observations of how things are moving in galaxies at larger scales, the cosmological scale. There are many things that we have to sort of modify in order to sort of make Newton's theory work. I mean, like adding things like dark matter or dark energy, which are things that we don't fully understand and which are an indication that maybe this new theory of gravity makes better predictions than Einstein's theory will do.
All right. I think we are towards the end of the introduction, the recap. So I see some questions from the audience, and someone asks how we actually detect the gravitational waves.
So maybe I can show again.
Yeah,
so
go ahead.
Gravitational waves are slight distortions of the space, and it's the space and time, as I said, is curved. But also, when a gravitational wave passes by, it means that certain distances in one direction get smaller, in other directions gets larger, and that changes in time. And so, what people do is they measure very precisely the distances between objects. They use this what's called an interferometer. It's some way to measure distances very precisely, and you do it in two perpendicular directions, and then you can see that when these gravitational waves pass by, that there's some distortion of space that should have a certain pattern that is describing exactly these waves that are produced by colliding black holes and things like that. So people have recognized events that are going on somewhere in space. And they do this not in one position on planet Earth. They have various locations where they have now these gravitational wave detectors, and that helps them to pinpoint the direction where these waves are coming from. It's like doing a triangular measurement where you can eventually find out where the wave has been originating, and this is where then this event of these merging black holes must have happened. And by now we have already about 80 or so of those events, and it's increasing every time again. And so we have learned a lot about black holes and their existence. And indeed, well, gravitational waves now help us even understand more about what's out there, because they give us another way of looking at the sky out there, because it's like adding a new well, how should I mean, it's like adding ears. When you have only eyes first, you can also now hear what's going on, because it's like having sort of sound waves being added to the spectrum of normal light.
I see. We have another question. So how did Einstein actually know that objects can't travel faster than the speed of light?
So this had to do with, yeah, I mean, the theory of light was developed, well, like 50 years before Einstein started his research by Maxwell, and he basically, these equations show it, but there's some way in which, yeah, he showed basically that light is sort of the thing that you can use sort of to synchronize clocks. And he had a theory of what space and time was about, that basically showed that being able to move faster than light requires you to sort of accelerate, well, or have a mass even that's infinite. I mean, you have to put in a lot of energy. Basically, when you start accelerating, it followed from his theory that eventually you cannot pass through that limit. But I have to say that there's a part of the theory that he developed which is based on what are called postulates. I mean, one of the differences between a mathematical theory and a theory of physics is that sometimes in theory of physics you have to start from certain assumptions. And you might actually say that the fact that you cannot move faster than the speed of light is sort of built into his theory by one of the assumptions that he made. What he basically said is that, namely, that if you measure the speed of light, if you do it while sitting still, or if you do this while even moving yourself, the speed of light is always the speed of light. And he basically says there's no way that the speed of light changes, even if you start moving yourself. And that is what's called a relativity postulate that he had put in, or a light postulate. And those two postulates sort of determined what the theory is about. And eventually it produced also all kinds of results that could be verified also with experiment. So it was pretty clear that his theory was eventually correct, also because it was confirmed by direct experimental verification.
Back to the topic of Einstein, Professor, you mentioned earlier that two cases where Einstein's theory is lacking is on the very small scale and on the cosmological scale.
Yes.
Do you have an example of certain observations that illustrate where Einstein's theory falls short?
Well, I mean, one thing that I can tell you about is the fact that we have in our universe objects that are rotating. I mean, like I mentioned the word galaxies. Galaxies are objects where we have stars, many stars circling around the center of that galaxy at speeds where you can even calculate how much matter is needed to keep that matter, the stars in the galaxy. It turns out that if we only look at the matter that we observe, that we cannot explain what is going on there using Einstein's theory. And so one of the modifications, and maybe I can indeed show a slide of this. Yeah, I need to go to the, can I share a screen? Oh, sorry. Share screen. So this is one of those galaxies you see here on the left, which is an object that is rotating so that this is the center, and then stars are moving around that center. And what is plotted here is the velocity as a function of the distance. Einstein's theory, if you only look at the visible stars, would predict that the velocity would fall off with the distance. And it would predict this dotted line. Well, what's being observed is that the velocities stay constant, basically. And so there's a lot of extra matter needed in order to explain this difference. And so what people have been doing in order to fix kind of Einstein's theory is saying that a galaxy is not sort of isolated stars moving around each other. There's some halo or some cloud of unknown particles, which is called dark matter, that have to sort of surround this galaxy in order for Einstein's theory basically to work. So we have no evidence of this matter directly, but we need to include it in our description if we want Einstein's theory to work. And so this is something that many people see now as evidence for the existence of dark matter. But if you look at it, well, honestly, basically, this dark matter is required in order for Einstein's theory to still work. And so this is a question that we still need to sort of answer is what is really going on here? Is there indeed is there indeed dark matter? Are there particles that can be found that explain this phenomena, or is there something that is going on with the description of the gravitational force? And in that case, it should be that Einstein's theory needs modification. So this is one of the phenomena that we are talking about, and also other things that I mentioned about the expansion of the universe that we also don't fully understand. Other things that happen at very short scale, distance scale, is that Einstein's theory also predicts that certain things go wrong when we go inside black holes or at the beginning of the universe. There we have that space basically stops existing. I mean, we call this either the Big Bang or there's something called the singularity. And this is again an indication that Einstein's theory doesn't explain everything. And there are points where Einstein's theory needs well, modification or at least an extension that includes quantum mechanics.
So these are the consequences that have led people to look for new explanations. Is this also the theory that you have been working on? Is this how does that one come to be?
Well, and then I have to go back to the black holes, and maybe this is a good point to indeed tell that story. Black holes, as I already indicated, they are objects where light cannot even escape. Let me go back to that picture. My mouse is still here. Oh, here it is. Yeah, so this is a black hole where I already showed the picture that it sort of is an impression of what happens when matter comes together. Then there is a certain surface, sort of an imaginary surface around that matter, where if you go beyond that, that light cannot escape. We call that the horizon. And the size of this horizon is determined by how much matter goes in. And what happened around, well, 40 years ago is that people started wondering about the properties of black holes, and many people know the name of Stephen Hawking. So Stephen Hawking was one of the scientists who started worrying about, so here's a picture of Stephen Hawking and with Penrose, who got actually a Nobel Prize for his work on indeed proving that there are these singularities inside black holes. Hawking worked with him, and they started worrying about what happens to black holes and the sizes of their horizons. And they discovered that there are certain properties of black holes that are kind of magical. I mean, maybe I should indicate already this fact here. I mean, this is a picture of a black hole where you also see the curvature of space-time that's being created. So you can think about a black hole as an object where matter has been sort of sucked into a point where the space starts curving so that you get basically a hole in space where things may disappear into. And then this horizon is one of these circles in this picture around it. Of course, the horizon is actually a sphere, but can be drawn a little bit more difficultly. So it's not, this is a picture you should think about as just describing the geometry of the space in the neighborhood of this black hole, where we only are viewing a two-dimensional plane. And so what happens near these black holes, and that's something that Hawking discovered, is that there are quantum effects. So we want to include eventually quantum properties of black holes and of the space-time. And in quantum mechanics, it's possible that particles can be sort of created by the uncertainty principle out of the vacuum. And what Hawking discovered is that there are many things that black holes do that sort of very similar to what we know as sort of the laws of thermodynamics. So maybe I should show that in the next slide. So what Hawking discovered is that particles can sort of escape black holes by making use of this quantum uncertainty. And black holes, they have a temperature and they emit certain radiation that's called Hawking radiation. And this eventually is a clue towards a new theory, because it basically tells us that gravity has properties like thermodynamics, and basically tells us that there are things that we can understand about the origin of gravity in a more fundamental way by thinking about what space and time itself are made of. A central notion there is what's called entropy, because in thermodynamics we talk about temperature, but also about a quantity called entropy. It's kind of the measure of how much, well, information, or how much how much information you can put in a certain part of your system. Like if you have a gas of particles, I mean, we talk about its temperature as being a measure of the energy that's in there per particle. And entropy is something that is associated with how many different possibilities those particles can be in. And for black holes, there's also the same quantity. And Bekenstein and Hawking together discovered that this entropy is proportional to the size of that horizon. And for us, this discovery by Bekenstein and Hawking about 45 years ago is basically the starting point of the new theory that I'm talking about, in the sense that it shows us that we can try and maybe explain where gravity comes from, just in the same way that the laws of thermodynamics can be explained by thinking about objects, gases, in terms of molecules and atoms. So the new theory of gravity that I've been working on is a theory that makes use of the ideas and the concepts that were also introduced already by Stephen Hawking and by other researchers in the 70s and 80s, and eventually developed into a new understanding, actually, of maybe even deriving the Einstein equations from the laws of thermodynamics. So we have made a lot of progress in the last 40 years in using these links with thermodynamics to understand, have a more fundamental understanding of where the gravitational equations come from that Newton and Einstein both wrote down. In the same way that we understand eventually the laws of thermodynamics as coming from sort of a statistical description of atoms and molecules.
And is this use of thermodynamics, is this acknowledged in the field already, or is everyone looking in the same direction, or?
Yes, I mean, by now, yes. So I mean, the ideas of Hawking wrote this paper in 75. So this formally goes back into that last century. But after that, a lot of progress has been made by people that worked on what's called string theory. But in the last 10 years, actually, I wrote a paper in 2010 that sort of emphasized the role of entropy in this gravitational understanding gravity. But it was already building on ideas of Hawking, a colleague called Ted Jacobson, and other people like Gerard Hooft, who've done important work. But eventually, in the last 10 years, it has sort of taken a lot of more progress and more people even taking that same idea seriously. So the idea that we can derive the gravitational equations from the laws of thermodynamics is kind of central in my field right now, and I think it's been studied by maybe hundreds of researchers around the world, and it's clear that we are on the track of a new theory there. So it's not like it's a question. I think we have already many elements of the new theory, but it's not completely finished yet. And it's maybe the same as with quantum mechanics. Quantum mechanics also started with an idea from Planck in 1900, and it took 26 years before people eventually had the complete theory. And I feel we are sort of in a similar stage where we have already some elements, and we have worked on the theory for some decades, but we still may need another 10 or maybe 15 years before the theory is complete. But that there will be a new theory explaining gravity from a thermodynamic point of view, I think it's pretty clear now. And indeed is kind of generally accepted in the field.
And what position does the theory that you have been working on, what kind of position in all this is it taking? Are your ideas, besides the thermodynamic part, are your ideas similar or compatible with other ideas in the field?
So they are compatible in many ways, but there are certain conclusions that I draw from it, which is slightly different maybe from what other people have been doing. One of the main differences is that many people see kind of that there's an equivalence between Einstein's theory and these thermodynamic equations, while I'm saying, well, now Einstein's theory should be sort of derived. It's like what is called emergent. It's a theory that doesn't need to be assumed to begin with, but you can derive it from this thermodynamic underlying description. I think more people are taking that point of view, but certainly when I wrote that paper 10 years ago, it was not the prevalent view. The other thing that I've done is that I have been thinking about how this theory should be developed in a universe which has this dark energy in it. Dark energy is an energy that we can see in the cosmos that should be there. And it also gives rise to a horizon, but not a black hole horizon, but for a cosmological horizon. And when you take that into account and use these thermodynamic equations, I propose that indeed we can then explain what we've been observing in these galaxies, these rotations of galaxies that need now dark matter can then be explained without the necessity to add dark matter to the theory. This is something that, well, people have not yet fully accepted. I mean, it's something that is a proposal right now, and it certainly requires more study to sort of get this into the complete theory. But it's something that I've worked out and also have made, well, contributions to in terms of equations, but which is not yet seen as sort of part of the full theory yet.
A question regarding the thermodynamics and its relation to gravity. When you say that that gravity is derived from thermodynamics, is this an analogy, or do we literally mean that thermodynamics, which is this statistical product of the interaction between particles, and this leads to gravity?
So thermodynamics is a general. So there's thermodynamics is a set of equations that can be written down, but they have an explanation from what we call statistical physics. And statistical physics assumes that things like gases and fluids are made out of atoms or molecules. And then you treat those atoms and molecules in a statistical way, and then you can derive those equations. The method by which we do it is very general. It doesn't even need to know that much about what atoms and molecules really are. So now we need a similar theory for gravity. And then the only thing that you need to change is then, instead of talking about the molecules and the atoms of a matter or some fluid or a gas, we have to think about the fundamental building blocks of the elementary building blocks of the space-time itself. And so these are not particles, they're not molecules or atoms. There's something else. I mean, they're basically bits of information that we have to start from. You even have to include quantum mechanics in there, but then after that, you basically can follow the same methods that we have developed, like statistical physics, to derive these equations of Einstein. So it's not like we need a lot of new math there. We basically have to have the correct description of these microscopic building blocks of space and time. And so we have to make sort of an analog of a hypothesis that there are atoms. We have to think about the atoms of space-time itself. And then the logic and even the steps that we need to apply are the same as the ones that we need to derive the laws of thermodynamics. So the analogy is there, but there's even more than that, in the sense that the actual mathematics looks is basically the same. So the difference is only that we're not talking about molecules or atoms of material objects, but we're talking about the building blocks of space and time itself.
All right. Yeah, it's tricky stuff, I think, for some of the viewers. But without going into too much theoretical detail, I believe that there has been quite some criticisms on your specific hypotheses. How do you, like, one of them is, I believe that it's very difficult to test in experimental way. How do you regard those criticisms? Or
so one of the things that well, first of all, any theory of quantum gravity is difficult to test. I mean, I'm now part of a group of researchers that tries to think of the experiments that might do this, but we have the problem that the scale at which quantum gravity becomes important is very short. I mean, you have to go to very high energies, or you have to look at very short distances that are not yet accessible with our current experiment. Or you have to think about clever experiments that use, well, indeed, cosmological observations or observations that are designed to sort of have, well, collected a lot of these small deviations of Newton's theory, of Einstein's theory, to sort of be detectable. Anyway, so this is a criticism I think you can apply to any theory of quantum gravity. It's not specifically to mine. I think the main question I got asked was whether my theory would be complete as a full theory, and I never said it was, actually. And some people have maybe presented this in popular articles as if it's the case. No, the theory needs to be further developed. And actually, as I once mentioned, I mean, there are many people working on theories of quantum gravity, and I feel we all have some ideas that go in the right direction. But eventually, the full theory will be constructed by combining all of our ideas. It's not like I have written down the complete theory, and neither have other people. I mean, we are working together on this sort of to find eventually this new description. And if you look at it at the end, you will notice that many people have done certain parts of it, and I think my parts will also be sort of recognized in that I've contributed to the new theory.
All right. So you believe that eventually a lot of people's work and your work might together create the new consensus, so to say.
Yes. The other aspect that I mentioned about these galaxies and dark matter, I mean, that's more specific to the things that I've been proposing. And there I actually think there's lots of observations that people are doing. But there, the theory itself needs to be developed further so that we can indeed make very specific predictions that are, well, distinguishing this theory from any other model that people have sort of made from, well, assuming this dark matter or these particles. So there's some way that question will eventually be solved by observations. But that may take also still a lot of time before people reach the consensus on what these observations imply.
All right, thank you. And would that consensus mean the end of dark matter?
Well, if I'm right, it would be. And actually, it's true that people have a very hard time looking for dark matter. Let me stop share, by the way. The original proposal, and actually the most promising theories that people put forward, predicted particles with certain properties that are called supersymmetry, and they have to appear at certain masses and with certain interactions that they should have, and that actually has already been excluded by experiment. So people had to already adjust what would have been the most likely theory according to their assumptions. So there's clearly a question and a puzzle there. I mean, people have been clever in putting forward all kinds of other particles, or they can talk about now about maybe there are some tiny black holes that make these dark matter particles. Anyway, the theories are more than there are even answers. I mean, it's in that sense, it's a bit of a wild landscape of theories out there that needs a lot of time before we can sort that out. I hope that when we understand gravity better, that the theory will be so compelling and convincing that people take it as the logical explanation because of also theoretical reasons. But that will take a lot of time because a lot of investment by other researchers in this dark matter idea has been, well, there in the sense that people are not likely to let go of those ideas, which maybe brings us also to sort of more the sociological aspects in how you do science. People have different points of view that also come from a certain background and a certain investment in their research that they are, well, find hard to give up.
Yeah, I can imagine the longer they don't find any particles causing the dark matter, the more likely other theories might get.
Yeah, so negative results are also important, which is actually one of the things that happened in Einstein's theory. I mean, there was a theory before Einstein developed special relativity, which is called the theory of the ether. So, which was some kind of fluid people thought was in space, where which determined the medium in which light was moving. And so, in that description, light would have different velocities depending on how you move with respect to that medium. Now, that was excluded by experiments. And this is sort of what made Einstein also develop his theory of special relativity. Actually, this would have been an answer to the earlier question. But this is just to show that a negative result can also make people throw away old theories and then embrace a new kind of theory.
Okay, thank you. We'll be moving on to one audience question. One audience member asks, concerning dark matter, what are your thoughts on the news that a neutrino has been weighed?
Sorry, that a neutrino
Has been weighed.
has. Sorry, I didn't get the full sentence.
Has been that the news that a neutrino has been weighed.
Yeah, I think I read today on the news that they had the weight of a very small.
So neutrinos have a certain weight, but I think neutrinos already have been excluded to be able to explain all of dark matter. There's one kind of neutrino, which is called a sterile neutrino. People have been trying to look for it, but it has not been found. But the neutrinos that we know about, and they are making part of what is called the standard model, they can have a small mass, and they will add to the weight of the universe, and they will do something in terms of adding what you might call a dark component, but it's not sufficient to explain all of these observations. I mean, it's not the dark matter particle. I think that has already been ruled out for a number of decades. Actually, I didn't see that news, but anyway, it's an exciting. I mean, people expected it, but they've been looking for certain evidence of it. Yeah, but neutrinos having weight is an important discovery, but it will not explain what dark matter is.
On the topic of dark matter, you mentioned that people are reluctant to give up on this theory. Do you think this is a serious issue? Do you think this is something that gets better with time, or are scientists always going to be holding on to old theories?
Well, I think it's always happened. I mean, in the time that quantum mechanics was proposed, even Einstein had trouble accepting the theory in its full generality, and there's some people that always resisted it. So new theories are not immediately accepted by the full community, and but also having a consensus. There's some way in which people follow logical reasonings that they then sort of believe in, but there's no direct evidence. But then they keep working on it, and then it's very hard to let go of that idea. I mean, so that's something that people have to accept, that there's some what is called confirmation bias, in the sense that people are looking for more arguments in favor of this hypothesis, and they're kind of blind to the negative outcomes. And so we have a lot of puzzles still in understanding our universe and what it's made of, and there's also discrepancies in how the theory is used to describe things that happened in the early universe and current observations. So, for instance, there's no consensus on how fast the universe is actually expanding now. There's some way that the stars are moving away from us. The way they do this is described by what's called the Hubble constant. It tells you basically how fast things are moving away from us depending on the distance. and that has been measured in different ways, and the outcome is different when you measure it nowadays, or you measure it through the indirect observations of the early universe. And this kind of puzzles, I think, indicate maybe that there's something wrong, but people are very reluctant to accept this, and they basically will try to looking for a fix again of the theory by making further assumptions about what either dark matter is or what this dark energy is. And it's in this way that they keep sort of an old theory alive by fixing it every time with new added elements.
As a scientist, why do you think people are so reluctant to give up? And do you think this is something that physicists specifically do, or do you think physicists are maybe even more humble than the other sciences?
No, I think the physics actually, of course, has been developed for quite some time. It's one of the older sciences in the sense that we have already been able to find a very successful description of many things in nature. And Einstein's theory also has been so successful in many circumstances that many people take it to be sort of the absolute truth. It also has a certain beauty to it. And so people are also reluctant to let go of such a theory unless there is eventually a compelling new theory. And although what I'm saying is that we are on the verge of sort of, or maybe on the way of finding such a new theory, and it's not yet in the form in which it can be sort of compete with Einstein's theory in its completeness. I mean, there's some way in which a theory has not been finished yet. It's not the same compelling nature yet. And so there's some way in which we eventually have to accept that maybe Einstein's theory needs to be replaced. But also the community that's working on this aspect that I'm telling you about trying to find this new theory of gravity is well, rather large, but it's not the full community in physics. I mean, there are many people working on these problems in cosmology and so on that are not thinking about the questions of trying to think about this new theory. And so there's also a lot of unfamiliarity with these new ideas, that people are not willing to accept new ideas so easily. So that's what I said goes back to this other point, that if you have a new theory, there are many people that are sort of still holding on to the old theory because they simply didn't keep track of what was really happening when this new theory was being developed.
And are you convinced that your ideas are correct, or are you open to be to be changed of mind?
Well, what I've tried to do, of course, is being very self-critical also about my own ideas. I think I've put forward elements of what is in the new theory, but how it eventually comes in. Of course, I'm open for discussions, and if people have criticism, I listen to that. I also think that well, what I certainly try to do is incorporate also ideas that other people have been developing. I think it's important to do this together and also be honest to what ideas other people have and how they sort of fit together. And as I said, I mean, I've been using ideas of other people, and I'm currently doing the same thing. So this idea of how dark matter is described as a proposal I wrote down, a theory that I wrote out about 3.5 years ago. But since that time, I've been also working on other aspects of understanding gravity, which is following other people's ideas and trying to learn about what they're doing. Also because I think it's important that, well, maybe to make the next step, I need to incorporate these ideas. So it's not like I can simply work on my own theory and ignore what other people are doing. I think it's something that we do together. So the idea that physics is people sitting in their own rooms and each one of them thinking about their own theory, and then we start comparing them and then there's a winner or something like this. This is not the correct picture. I mean, we're working together. And as I said, many people have good ideas, and eventually you would like to see how they integrate into one theory that we eventually all accept as being the right theory. And in the end, many people will have contributed to that.
All right, thank you. That's very clear. You just mentioned that some people tend to take Einstein's theory as the truth almost. So on a more philosophical note, what would be the significance of having a new, better theory of gravity? I can imagine that it gives rise to certain new applications, but in other words, does a new theory of gravity improve our understanding of the universe?
Yeah, that's certainly the question I think that's driving many scientists is eventually where does this whole universe come from and how can we understand its origins and maybe how it's developing in the future. And I think we have just, as humans, a question, well, we like to know these questions. And I think it also helps us understand our place in the universe, because I think many people in the street, if you ask them about, well, the Big Bang or anything about what the origin of the universe is, many people know about it. It sort of gives us some perspective on well, the universe, that it's big. I mean, that there are stars out there and that we can explore space and that we can go to other planets. I mean, we have some like to know our place in the universe, which is not just about our daily life. It's something that's bigger than that. And so a theory of gravity that goes beyond what Einstein already told us about will indeed improve our understanding. And it also, I think, will change, how should I say it? What I actually think is that this new theory will not again be the final theory, because when I started working in my career, it was people thought there would be a theory of everything that would be the final theory, that we finally understand how everything works. I don't think that will be the case. I mean, as humans, we have to be a little more humble, that we can understand more and we can understand things better, but it's not like we can understand everything. And so I hope that we can learn more about what the universe is about and understand how its origin sort of should be explained. I think that the theory of the Big Bang, for instance, will be understood in a much nicer, maybe better way. Now it's something that is kind of a little mysterious, as something that happened or some phase where suddenly things started exploding and so on, which I think is a description that eventually will be replaced by something that kind of mathematically might be kind of equivalent, but I think it will be more appealing in the sense that our universe didn't originate from nothing. I mean, the feeling of a Big Bang is almost like there was nothing there and then suddenly it exploded, which I think is unsatisfactory. And so the understanding of where it sort of originated from will improve with our new theory of gravity. And I hope that sort of gives some satisfaction also to people in general. I mean, that we understand better the origin of our universe.
Mm-hmm. But you don't think we can ever describe the whole universe in mathematical equations?
I find that hubris, in the sense that our intelligence is better maybe than some animals in our planet, but it's not like it's infinitely better. I mean, I think the idea that we as humans would have reached the level of intelligence that we can suddenly understand everything about our universe is appealing, and it certainly has motivated a lot of research, like the search of this theory of everything. But it's also a image that we put in front of ourselves that I think is overestimating our capabilities of understanding.
But is it then even important to improve your idea of the world if it's never going to be describing everything?
Yeah, I think we can understand things better, and there are certain consequences of this. And I feel that as I said, every old theory eventually will be replaced by a new one, and going to the next layer in that description, I think, is an important step. I think it also unifies a lot of things about our understanding. I mean, for instance, we don't understand gravity and quantum mechanics together in one. We will make that advance. We can eventually have a more complete description of everything. and indeed apply it in situations where we have not been able to apply the old theories. And one thing that actually happened with old theories that were replaced by new ones often is that we didn't even know what were the new predictions we could make. It's only after the theory was there that it became obvious that the theory had certain consequences that we could measure. And so there's sometimes questions that we haven't even thought about that suddenly become obvious that we can answer them.
Okay. Yeah, one question from the audience that is related to that is from Wim. And he asked, where are the borders of the knowledge of the universe? We cannot know all, but what can we know?
Yeah, I don't know exactly. I mean, what is it, the border? I mean, because I said, I think we never will know everything. I mean, one of the things that I think it's going to be very difficult to answer is why there is something instead of nothing. I mean, why is the universe there anyhow? I mean, also the size of the universe, it's incredibly large. It's very difficult to understand why it should be so large. But I also mentioned the example of what we can do with thermodynamics. I mean, we can derive the laws of thermodynamics, assuming atoms and so on, but we don't need to know what these atoms really are. I mean, we know about the periodic table, but the periodic table tells us what kind of atoms exist, but we don't need it to derive the laws of thermodynamics. So the same thing, I think, is true eventually with our universe. I think there still will be certain building blocks that we have to postulate that there should be there, but I think we'll never discover what those microscopic building blocks really are. I mean, there will be a limit to what we can understand about that, but that doesn't prevent us from using it, their existence, to derive a new understanding. I mean, we can derive the new equations without knowing the details of the microscopic theory. And so there will be things always hidden from us, but it doesn't prevent us from understanding a lot of things about what we are observing and how our world sort of hangs together.
Okay, so that's quite a pragmatic approach.
Yes, that's exactly why I take a distance from people that say that we eventually understand everything. I think we'll understand more, but we don't need to understand everything to still understand a lot.
There's another, it's a different question, but nonetheless interesting. The phenomenon of entanglement, is matter or energy involved, and how so?
Very deep question. I mean, I didn't mention that word. It's indeed one of the central elements in how we are going to develop this new theory. I talked about a bit about entropy and so on, but the microscopic description of the space and time indeed involves quantum properties, and in particular is entanglement. So what is entanglement? Just for the audience that don't know this. So I said that quantum mechanics, if we do our measurements, the outcome are not totally certain. I mean, for instance, if I flip a coin, I don't know whether it's heads or tails. But with entanglement, the funny thing that happens in quantum mechanics is that if I have two coins, one here and one very far away, I can flip the coin here, and then it can be heads or tails with sort of chance a half. But the entanglement tells you that whatever happens here is going to determine what is the outcome on the other side. And so these two coins then are entangled in the sense that the outcome here, if it's heads there, it may be tails. And if it's tails here, it should be heads there. That's called entanglement because these two objects, their uncertainty basically is connected. Now, this is, I mean, maybe I should go back to what was the question about this, because
if matter or energy is involved.
Yes, so matter is, of course, a property that, I mean, has properties that can be entangled, but the concept of entanglement is actually much more general. But actually, entanglement can be measured just abstractly in terms of what's called, again, an entropy. But it's also true that there's some form of energy associated to that. I mean, there's some energy that is derived from entanglement. There's even a paper written 2 years ago that basically has the title that energy is entanglement. There's some way that energy is a concept that was introduced, but eventually we want to understand where it comes from. And then it seems that entanglement is the more fundamental notion. And so it's almost like we have to start from this, well, quantum uncertainty and the entanglement in that. And then we can understand things about space and time, but also about energy and other properties of matter. So matter basically is then derived from these more fundamental descriptions. And so matter and energy should then be seen as emergent themselves and not as something that is fundamental in the description of what our world is about. And the same is true then of forces. I mean, this is, I hope that is kind of clear in what I've been telling you, is that forces which are now assumed to be sort of there by assumption, I mean, that's what we call a fundamental force, eventually don't need to be assumed. They can be derived, and they also are then a consequence of these changes in these entanglement properties of space-time. So we start from a much more basic language that doesn't involve matter, energy, or forces. I mean, those are concepts that eventually can be derived.
Nice, thank you.
A question from Kai. Is there a relation between your theory and string theory?
Oh, yes, there is. I think string theory was certainly the way I also started out my career, because it started to try to answer also the question about how to combine quantum mechanics and gravity, in particular general relativity. And it has made important breakthroughs also in explaining aspects about black holes, about where this entropy comes from, but it's not the complete story. And it's precisely in the last 10 years where we are understanding more aspects that are related to this entanglement and so on, and information. But eventually those two descriptions and the string theory picture sort of has to, or a string theory description, I should say, should eventually become part of the same theory. So I feel that what I just said about being matter and energy being emergent, there's some way that even the way that we now are thinking about string theory will eventually be, well, either be derivable or being unified with the way we think about this quantum, this more microscopic description. I feel that string theory may be eventually the language in which we can do it, but I think it's still something that might eventually be, how should I say this, derivable. Actually, I'm now working on a paper even doing this, where we start from something much more elementary, having to do with just, well, a quantum description of some microscopic system. And then eventually we see that string theory somehow emerges again from that description. So there's some way that even string theory can be explained from this more fundamental picture. But it also contains certain clues in how to develop the theory. So it's an important part of what the new theory will be about, but we have not understood how to put it in the story yet.
Okay, thank you. And one last question from Henry is that in Einstein's theory, gravity was considered a distortion of space. What role does time play in your theory?
So time, you said, or?
Yes, time.
So there's space and time. I mean, Einstein sort of realized that space and time basically form different aspects of the same object that he called space-time. I mean, in Newton's theory, time was kind of absolute. I mean, everyone agreed on what time was, but in Einstein's theory, time is also relative in the sense that clocks for different observers can move at different speeds. So one thing that we start understanding now is that microscopically, neither space or time may exist. I mean, it's some way that they both sort of come to existence by making use of, for instance, this entanglement, this quantum entanglement. So one question that we can ask then is, for instance, if we take space, why is space, when I think about the middle of space, sort of why is the right and the left, are they connected to each other? There's some way in which entanglement plays a role in that. Maybe since I have maybe, how many minutes do I still have? I mean, like 2 minutes, maybe? Yeah, I can show a short, I want to actually show maybe a small slide, which kind of, how do I do this? Here we go. There's this story. There's something here that happens with black holes. One thing we're learning basically is that black holes can connect, they can glue together two spaces. I mean, there's this throat, I mean, this hole that I showed you, but it actually, when you go through it, you actually end up in another universe, which are glued together at this, what I call the horizon. And we now understand that this actually comes from an entanglement between what's happening on this side and this side. It's almost like entanglement allows you to make space connect to each other. And so it's like the glue that makes space-time hang together. The same happens actually with time. I mean, some time actually is also something we can eventually understand from entanglement. And so time can be also eventually derived, but it's a different object than space. I mean, we even in the theory that I'm developing, space and time are not the same thing. They play a different role, but eventually they sort of must emerge together into what we call then space-time. Anyway, I don't think I can give you a complete answer, but certainly time is something that is emerging, and also space is emerging from something that's underlying it, where space and time neither of them is being assumed to begin with in the beginning.
Okay, thank you. I think that did partially answer the question quite well. But now we will be wrapping up. And during the course of this interview, many interesting topics were discussed. Professor Verlinde, for the curious watcher, do you recommend any sources where people could learn more about the topics mentioned?
Well, I mentioned something about quantum, what's called quantum information and gravity. I mean, there's a lot of popular literature out there. I mean, the internet is a big world where you can search for these things, and you will see that the developments I talked about are being described in many popular sources. I don't think I know one particular one. I mean, it's just the relationship between entanglement and gravity. You just put it into Google and you'll find many descriptions there. I mean, many even accessible accounts of developments that are going on. And you will see many of the names that I already mentioned in other researchers that have been doing work in that area. And if you see that actually and read those accounts, you will actually understand why I say that there is indeed a new theory that's going to be emerging. I mean, going to be appearing of what gravity is about. And the word of emergence of gravity actually is also central in that, which is a thing that I contributed to, I think, mostly, in the sense I made people aware that we should think about this new theory as a new way of explaining what gravity is, instead of having to assume that it exists right from the beginning.
Thank you. That will be the end of this interview. We'd like to thank Professor Verlinde for his time and his, let's say, well of knowledge. Regarding the next beta break edition, I think this one will be very interesting, and its topic is related to depression among students. So anyone interested should stick around for the next edition.